So chapter 5.6 discusses graphing rational functions, and we usually do this in steps. So the first thing we can look for are roots, and these are our x-intercepts. And we can find this by setting the numerator equal to 0 and solving for x. And then our answers are going to be in the form, whatever your solution is, 0. Our vertical asymptotes are essentially restrictions on the domain in the graph, because wherever we have these vertical asymptotes, they are x values that cannot be used because they yield y values that may be undefined or imaginary. So we usually just set the denominator equal to 0. Because let's say, for example, we have 1 over x plus 1. Then if we say x equals -1, then we have 1 over -1 plus 1, which is 1 over 0. And since we cannot divide by 0, if x is -1, then y is undefined, which means we can't use -1 in our equation. So that's one of the restrictions for the domain. And then our answers for the vertical asymptotes are going to be x equals whatever we solve for. And we may have more than one as well. Then the next thing we want to look for is our y-intercept. And this one is probably the most simple. All you have to do is set x equal to 0 in the function and solve for y. And then we want to take a look at our horizontal asymptotes. So we're given some rational function, which means we have a denominator and a numerator, and each one has their own polynomial. So we want to look at the highest power term for the numerator and the denominator. Let's say it's balanced, which means that the highest power is going to be an x squared, for example, or x squared. So essentially it ends up being, oh, you know what, that's probably wrong. So for case 1, the powers are going to be balanced, and what this would look like would either be some ax squared over bx squared, or ax over bx, maybe even ax cubed over bx cubed, whatever, as long as the powers, the highest powers, are balanced and they both have some coefficient a and b. Then our horizontal asymptote is going to be y equals this ratio a over b, and this is a constant. This a over b should be a constant, so it ends up being just this horizontal line. So our second case would be, so the example we're given here is f of x equals 4 over x plus 4 squared. And the first thing we can do is look for our roots, or our x-intercepts. And then we do that by setting the numerator factors equal to 0. And if we do that, we get 4 equals 0, which cannot be true. So we actually don't have any roots for this one. So this function never crosses the x-axis. Then the next thing we can look for are our vertical asymptotes. And we do that by setting the denominator equal to 0, the whole thing. So we have this x plus 4 squared equals 0. And then if we take root of both sides, then we just get x plus 4 equals square root of 0 is still 0. So then x equals -4. So we have some vertical asymptote at x equals -4. And this is true. We can check this by putting it back into the equation. So 4 over -4 plus 4 squared, it gives us 4 over 0, which is undefined. So that means that if we plug -4 into the equation, we get some undefined y, which means that our domain is restricted by this denominator, a -4. So then we look at our y-intercepts. And what we do is we set our x equal to 0. So we have 4 over 0 plus 4 squared. This gives us 4 over 16, which is 1/4. So we have some y-intercept at 0, 1/4. And the last thing we look at is our horizontal asymptotes. If we FOIL out this x plus 4 squared, it gives us x squared plus 8x plus 16 with the 4 on top. So if it's bottom heavy, then that means our horizontal asymptote is going to be y equals 0. So we can actually sketch the graph from here. If we have some graph, then it never crosses the x-axis, and we have a vertical asymptote here at x equals 4. We have y-intercept at 0, 1/4, so let's say somewhere here. And then we have a horizontal asymptote at y equals 0. And since this is 1 over x squared, then they're going to be on the same side. So our graph is actually going to look like this. If it was 1 over x, then it would be this way.